So we're in section 16.7 right now, where we're talking about weak acids and weak bases and relating those to Ka and Kb. And in this video cast, we'll focus on weak bases and their equilibrium constant called Kb. Just a tiny bit of chemistry in your everyday life again. Amino acids have an amine group in them. NH2 is the amine group, and you can see that in both of these example amino acids. And this is the portion that acts as a weak base. It's a getter of protons or an acceptor of hydrogens. And even though the molecules can get big and scary looking, just look for small pieces or small parts like this with NH2s on them, or areas with unshared pairs of electrons that are good places to accept protons, and then you'll know that you might be onto something called a weak base. So here's some notes about weak bases and just a little bit of review that we already gave as an example right here. Many, not most, but just many are amines. Many weak bases are amines, and they have a nitrogen with some things attached to it, and then an unshared pair of electrons. One of the simplest amines is called ammonia, NH3, and then it's got an unshared pair of electrons. Methylamine, or methyl ammonia, sometimes it's called, has two hydrogens attached to it, and then a methyl group. Here's another one that's got dimethyl ammonia, or two methyls attached to the amine group. And those are just a few examples of the amine structures. Well, besides amine, there are also lots of weak bases that are conjugates of weak acids. And so conjugate bases of weak acids are really popular. And here are a few bases that are from after they've released their protons as acids. So CO3 2- is a pretty good weak base. HS- is a pretty good weak base. ClO- is a pretty good weak base. These are things that are good getters of hydrogens, and you can imagine if they get a hydrogen, get a hydrogen, get a hydrogen, then they would become a weak acid. So here's just the general equation, or the general form of a base or a weak base. A weak base would be a proton getter, of course, and when it's dissolved in water, it gets a hydrogen from water and it becomes Hb with a positive charge, and then some OH- is formed. Going way back to the very first video cast in the definitions of weak acids, or just of acids or bases, it would increase the hydrogen OH- concentration in solution, therefore it's called a base. We could write the equilibrium constant expression for this, and the equilibrium constant would be products divided by reactants to the powers of the coefficients. Remember, don't put water in there because water is a pure liquid or pure solid. And one of the good rules in this chapter is when you're in doubt of how to start a problem, always react it with water. Always react whatever it is with water, whatever it is with water, whatever it is with water, and then decide, can these species be good getters of hydrogens, and then you're off to a good start. Appendix D has a listing of a number of Kb. This isn't a very long listing, but it's dissociation constants for bases, or Kbs, and there's a number of them listed right here. And it gives you their various rating scale of how strong of base they are. Remember, the bigger the number, the more dissociation there is, or the more getting of hydrogens there is, and the more ions that are formed, and therefore more products would be formed. So lots of times weak bases come from dissolved salts. Salts, remember, are ionic compounds that have a cation and an anion. And so identifying these things that have a cation and an anion, and then they break up, and then identifying them as weak bases is many times kind of tricky. The anion then is many times a proton acceptor, and a proton acceptor is, of course, a weak base. And so here's a few examples of this. And as soon as we're done with these examples, we'll go on to some mathematical calculations of this as well. So NaClO has a cation, Na+, and an anion, ClO-, and when they break up, this ClO- can act as a base in solution, and ClO- is a good getter of hydrogens, and therefore it is a weak base. And you can see the reaction, or the equilibrium reaction right here with water. It gains a hydrogen, forms this conjugate acid over here, and it increases the concentration of OH minus. How do we know that this is going to do that? Well, you have to look at where ClO minus came from. And if it came from something that would be a weak acid, then it would be a good getter of hydrogens, because if it's going to form a weak acid, remember weak acids don't want to dissociate very much, and so then you know that this guy would be good at forming that weak acid. Here's a second example, K2CO3, and then it would form some CO3 2-. Now think in terms of this species right here. If you added hydrogens to it, would it be a strong or would it be a weak acid? And you know there's only 7 strong acids that you memorize, and so this would be a good base because it would form a weak acid when it would get protons. One more example, let's take a look at NaHS. NaHS would be one that would form Na plus and HS minus. And then ask yourself the question, if this would get hydrogens, would it form a strong acid? Well, the only strong acid you know with sulfur in it is H2SO4, and that's not going to form that. And so this would act as a good weak base, and therefore, when in doubt, react it with water, and then you'd get H2S and OH minus. Writing these equations is one of the trickiest things to do in all of chemistry. Let's look at the calculations. Let's look at the calculations that are associated with weak bases. And here's one called calculate the pH of a 0.65 molar solution of, this is called pyridine. This is a type of amine once again, and it is a weak base, and it has a Kb of 1.7 times 10 to the negative 9th. And we want to know the pH. Well, we did one like this last video cast where we found it for an acid, and I gave you 5 steps. And we'll do a similar piece where we have 5 steps here again. Step number 1 is to react the weak base with water. Since pyridine is C5H5N, I react that with water. I make it be the proton acceptor. I put an extra hydrogen either here or here. It doesn't matter. I put it next to the H because they know that it's an amine. But as long as you get it a positive charge here, that's okay, and a negative charge right here, because the OH minus is the thing we're really interested in to find the pH. Because once we find the OH minus, now we're into the pH square, and we can go here and here. Step number 2, make an ice table. So put ICE over here on the left-hand side, and then fill it in with the starting concentration, 0.65 molar, none, none, none. And use x's, so lose x, gain x, gain x, and as we did with weak acids before, let's ignore the x and call it small as compared to 0.65. So we'll end up with 0.65 minus x, x, and x, but we're going to ignore that x and we're going to say that he's small compared to 0.65. Next, write the equilibrium constant expression for Kb, so products divided by reactants, ignoring the x, would be x squared divided by 0.65. And this would equal the Kb, which is 1.7 times 10 to the negative 9th. And now we're going to solve for x, so multiply both sides by 0.65 and then square root both sides. I did this math for you already, and it ends up that x is equal to 3.32 times 10 to the negative 5th. And then lastly, this x right here is equal to the OH minus ion concentration. So we now need to find the POH and then the pH. And so on my calculator, I would want to do the negative logarithm of this number, 3.32 times 10 to the negative 5th. And that would give me the POH. And so the POH would be equal to 4.47. If you're wondering where that calculation came from, remember I found the OH minus and I went to the POH right here by following this arrow. And now I can go from POH to pH, knowing that pH and POH add up to 14. And so 14 minus this gives me a pH of 9.52, which makes sense because we know that on the pH scale, things way up here around 14 are very basic, 7 being neutral and 1 or 0 being acidic. A pH of about 9 right here would make it slightly basic, and that would mean that we have a weak base, which we do. Good luck with your weak base calculations.